Very much for inviting me to give a talk today to the organizer, Heuritech. So it's my pleasure to be here. So I am Matthieu Cord. I'm professor in the University Pierre-Marie Curie, also called Paris 6 or Jussieu because it's close to the subway. And I am working in the LIPSIS laboratory, which is the computer science laboratory of this university. Right, it's about 500 people, okay, working there, 200 permanent people, and we are an organization in 5 departments there. And one of these departments is about data and artificial intelligence, okay, and inside this department we have several teams, and one of the team is the machine learning and information access team, which is led by Patrick Gallinari, okay. So Patrick is one of the father also in France of the neural network. So we have in this team a lot of things about neural network, and of course deep net now. Essentially at the beginning for text classification, but later for structure output. Typically, I mean for let's say structured document, web document, and then after for a different type of network. Let's say for instance for graph representation, learning on graph and things like that. Okay, so I think some typically also we have some things about reinforcement learning and deep reinforcement learning, and some of the PhD students had presented something in one of the I think the last meetup or the one before, I can't remember about that. All right. So for today, I'm going to work much more about visual recognition, which is more or less my field. Okay. And so we are going to talk about neural network and deep neural network for that, and of course, so then we have convolutional neural net to do that. Right. So and I want to make some connection with other kind of learning that we can have, typically what we call the weakly supervised learning in image recognition. So I'm going to explain there's two things and how we can connect both things together. Right. So our context is image classification. So let's say that we have one image, and of course here we can have multi-label, multi-class, whatever you want here. Okay, at the output. Right. This is and then in between we have something like neural net machines to do that, right? And this is more or less the state-of-the-art architecture to do that with deep convolutional neural net at the moment. Okay, so the other point is about what we call weakly supervised learning, because we know that for some of the category we are looking for, it could be very helpful to have some information about the geometry, about where is the data inside the image, how the information is localized into the image, okay, in order to do a better prediction. Okay, to better predict that there is a car inside this image, it could be very helpful to know more or less where it is, right? So the idea is to have this kind of bounding boxes, right, during the learning, and then try to learn the machine thanks to this bounding boxes, okay. And but it's very expensive because we have to label all the data and to localize all the different type of elements that we want to detect into the image, okay. So one thing to do is to just relax this hypothesis. All right, and just say, okay, I try to put into my computer, into my algorithm, something that will detect or what will give information, okay, this about typically where is the things into, okay. So this is really the framework of that I've been deeply studied, let's say in the SVM, so shallow classifier, I would say, and this is typically what they call the latent SVM that have been done to do that. So the idea is you have like a hidden variable that can tell you more or less where is the information, and then you learn both where it is and what is it in this kind of latent SVM framework, all right? And so the question is it possible to put this kind of things about latent variable into the DIP, right? And how to do that, right? So it's the connection between DIP and latent or weekly supervised learning things, okay? So this question is really, I mean, the main purpose of the PhD of Thibaut, okay? Thibaut Durand, my PhD student, okay? Who is there, I think, somewhere, okay, yeah, there. Right, and this is really, I mean, his work, and we are co-supervising this with my other colleague, Nicolas Tom, right? Okay, so let's say we take one of the best deep architecture we have, okay, on the table, right? So since the AlexNet, that was the first one to really, I mean, be successful for image classification task, okay, in 2012. We have several extensions of this kind of things, and let's say that the VGG is a very good one with that can be with 16 or even more layers into. We also have the Google net here, or the recent ResNet, which is quite more deeper. But whatever the architecture, we are going to consider that one and to see and to study how we can put weekly supervised into this, right? So to do that, let me first give few things about this standard deep CNN architecture, right? So from the image, you have several layers here. Okay, so usually here, this is the size of the image, and then you have here two steps where you have convolution plus nonlinear function that can be, for instance, the Rayleigh function for that, right? And then you do that two times, and after you do some max pooling that can also be the time to reduce by 2 here the size of the data that you consider, okay? So this is typically what we have here. And then we again have 2 steps of convolution, right? Again, with the same size. And then a new step of max pooling, okay? That give you the next reduction. And then 3 times of, again, convolution, reduction, convolution, reduction. And my point is to come here, then from here to here, then you still have some spatial information. This is 7x7 image, and you have 512 deep map here. Okay, and from that you are going to go to something which is very flat, okay, 1 by 1, and you consider, okay, let's say 4,000 filters to do that, okay? So that means that one filter to pass from this level to one of these here is something that is exactly the shape of 7 by 7 by 512, okay? And this size is fixed, right? Okay, so this is my point now. This is then you have a problem to introduce, okay, because of this fixed architecture, something that could be a different size here. So, okay, why? Because as I said, as it is fixed, so that means the 7 by 7 here, you can't move, you can change this thanks to this fixed architecture, right? And then when you backpropagate this information, you of course you see that here you are 14 by 14, 28 by 28, and so on. And so that means that with this architecture, the VGG, the size of the input is completely fixed. Okay, you need to have one image, which is 224 by 224. Okay, you have no choice about that, right? Okay, if you try to change this and you put this image into the VGG, okay, it will crash, because here you will have something that is different from that size, and so you will not be able to compute the filter right here. Okay, so the idea, if you want to change the size of the input in order to be able to see not the whole image, but perhaps a part of this image, okay, you absolutely need to handle with this problem, right? Okay, so here okay, I put a zoom just to explain, okay, how we can relax this problem. We have the fixed size normally, okay, and then the idea is that you still have a new sliding window approach with this kind of architecture. So that means that if your image is bigger, let's say for instance here something that will be with a y and h value for the width and the height, okay, then after you will keep the same architecture we had before, but you will be able to like a sliding window apply this everywhere, okay. And so that means that you will not get any more one by 4,000, but something that will be exactly the number of answers that you need to have to go through the whole part of this block, right? Okay, and then of course I didn't solve the problem at this point, so I need to add a new step, what usually is called about spatial aggregation, okay, spatial pooling, but it's not exactly as a pooling I defined before. Why? Because here the size of my pooling will change from one image to another, okay. As soon as the size of my input will change, okay, the size of this map will change, and so that means that my aggregation will work to different size as input, okay? Okay, but the point is very interesting here is that from that, okay, I am able to localize something in the image before this aggregation, okay? So that means that this block here corresponds to one part of the input, let's say one window, okay? And when I move into my whole image, I will move here in different block, okay, different blocks, right? So let me come back to the whole architecture. You have here the same kind of VGG, okay, but with the connection with the weakly supervised ability, okay. So it's exactly as before, okay, except that as you see, I do not consider here, okay, the previous image, but let's say like a much bigger image, okay, larger image as input, okay. So my network will be applied everywhere, so you can see that, of course, for efficiency as a much bigger convolution everywhere, okay, and pooling and convolution and so on. But as you can see, of course, the size here of the different map will be different than the one I presented before, okay, except when you just arrive here, okay, if I consider, for instance, C classes in my problem I want to solve, in the problem I want to solve, then here I need to pass from this H prime, W prime blocks, okay, of course, time C blocks, right, to the 1 by 1 by C, okay, thanks to my region selection I presented before, okay. Voilà. And that's all. Okay. So the way that you can really, I mean, put something, I'm going to show how to describe, how to illustrate the effect of that. But it's just to put a new, of course, a new step here, okay, doing this kind of spatial selection. So that means that here I still have some geometrical information about the content of my image, okay. And of course, there is, I mean, trick things here for the computation of the whole architecture, okay. So we can see one example of how this kind of things works, okay. That was the work from the Willow team, okay, in Paris with Ivan Laptev and Joseph Sivic, right? That did something more or less like that by choosing for the region selection, by choosing to take the max. Okay, so I mean, whatever the size, I just keep the max, okay, for this step, right? Okay, so what does it mean? Let me show on one example. I have my input image, and here it's one of the map corresponding to the motorbike class, Okay, so that means one here, it's one of the of this one map inside this block. Okay, and so when you have this kind of map, of course, I just put it at the side of the input, but it could be quite smaller, right? I take the max here, so I take the max over this this block, and then I just show here, okay, to what part of the original image corresponding the max I choose here, okay? And it's exactly something representing by this into my original image, right? So this is exactly, I took one max here to get my result and to do my classification, but if I see where it is inside this up to my original image, I will find this part, okay? Okay, so you can do better, okay? As instead of choosing just the map, we can do better, okay? And so I'm just show here how we can select something that it's more relevant to do the classification in a weakly supervised context, okay? So it's when you choose only the max, you lose a lot of information about what is around, okay, this max, okay? So let me show on one example. For instance, for this street image, if I already learn a street model, okay, and then I just ask for the max, so I have this kind of window size that is moving into my deep, right? And the best score is here, okay? That means that, of course, to classify a street, okay, having something which is exactly you know, on the middle, and you see the road, you see more or less the car, and of course you see also the horizon, okay? It could be good, so this is very high score, okay? And the color here, when you are red, it's very good, and of course when you go up to yellow and after to blue region, okay, it seems that you are not able to detect. I mean, it's like negative value for the detection, okay? And what Thibault proposed is also to add something about the contextual information, not taking only the max, but taking the max plus the mean. Okay, and so what type of information is into the mean is in the mean information is something like when you are in a street model, you try to enforce that everywhere you find something that is related to your class. Okay. You want to be able to say that even it's something that could not be, I mean, that could be the worth hypothesis into this image to be a street, okay? I don't want these things to be too bad, right? Okay, so here it's very clear, for instance, when you have a part of the road, it seems to be that it can be other things, but this is, I mean, certainly the less informative for having the street here, okay? But if you take the same thing, so I mean the same input image, and you try to see what happened on a coast model, I mean, if I already learned something that detect coast, of course, more or less everything is blue because there is no interesting information about a coast into my original image. Okay, but let's say this more tricky example where I try to learn and so to test a highway model. Okay, and so that means I already learned a highway model and I want to know if this image is a highway or not. Okay, then I am able to have a very good score for the max. Okay, why? Because if you see this kind of things, you see a street, you see just a few cars around, it makes sense that it could be a part of a highway image, right? But if you take also the information about the mean, then here you have a big trouble, okay? Why? Because it's very, I mean, a negative evidence of having a building facade, okay, into a highway. In a highway image or to detect a highway, okay? So by taking both information, that the max plus the mean, okay, you are able to be much more robust and much more efficient to detect different type of object into your images in a weakly supervised framework, okay? So you can do that instead of doing just I take a max plus the mean, okay, into my deep, right? And of course, I can also mix this with different tricks that I can have also is that we know when we are doing weekly supervised learning, which is very, connected to another framework, which is the multiple instance learning, okay? I have several instances, like a bag of a hypothesis. In my image, it could be all these sub-windows, okay? And from this bag of sub-windows, I want to be able to give the right decision, right? Okay? And we know in that case that it could be better, instead of considering only one, the best one, to take, for instance, the three tops, right? So you can put also this kind of things into your strategy, okay? So everything is here. The way I choose, okay, to pass from my convolution or from my maps, my different maps, to only one value, okay? And so you can do only max, you can do max plus mean, you can choose the k most relevant instances and so on, right? Okay, and then, okay, this is done for the whole architecture. Then you just have one question left, which is how to learn this kind of things, right? So we know very well, it's the classical objective function that we have. Whatever it is a deep or whatever it is SVM, you still have this kind of things with a loss function that you try to optimize on your supervised, so on your training example, okay? This is the supervised, okay, in terms of we have the labels, okay? It's weakly supervised because we don't have any additional information inside the image, but of course we have the label, right? The different labels. Then you can put some regularization term, whatever you want. And typically here, in our case, I just put this equation just to illustrate where I am in between the blue and the green part. And typically, as you can see, when you go from one map to another, you are changing the label maps. Okay, 2 minutes. Okay, right. Okay, and so W is represented this information moving from here to another, right? And the H is typically what we call the hidden variable, right? So you can choose a max over all the different hypotheses you have here, okay? This is for H, okay? And Y is typically moving here, right? And finally, there is no problem. You can exactly have this kind of things. You can derive, use stochastic gradient descent training. So it's more or less like the backpropagation that we have in a deep CNN, except that, of course, we only backpropagate the information for the winning window. Okay, so typically when I am here, the best window is here. It gives me the labels. Then I backpropagate from this label through my whole network. Okay, and of course I do it for the max and the mean if I choose the max plus mean selection, right? Okay, and the same for in the case where of course I'm trying to learn about, and of course I have some negative evidence. I will also decrease the score, of course, of this window. Okay, let me so quickly go into few experiments. So how we can evaluate this kind of things and to see if it's better than the traditional VGG, let's say. So we take a VGG, we can pre-train on ImageNet, and then we can fine-tune different things on several kind of data sets. So I just put different, so the VOC 07 or 12, MIT, and so on. So this is classical benchmark that we use for image processing evaluation for the classification. We also use the COCO one, which is the more recent, about 100,000 images, right? So I'm skipping these things, and perhaps just the take-home message is that when you just consider the VGG, the baseline without having this kind of weakly supervised strategy into the deep, okay? This is exactly the same deep, okay? Except that you put this kind of strategy I described before, you have a huge gain, right? Okay, huge gain for us at least. Okay, so it makes a real difference, and it's as well for the classical VOC dataset, which is more object recognition oriented. That for the scene recognition, it's exactly the same kind of things for 15 scene or MIT 67, right? And also again, even for this kind of VOC 2012 action or in the COCO dataset, we also have a big gap for this kind of things, just doing this or not, right? And to finish some few examples on how what finally the algorithm have learned, right? Let's see, for instance, if you consider aeroplane model, right? Here for this image for the aeroplane, so this is an image of aeroplane, so we should expect to have a good detection for I mean the free best window, okay, on the plane. That's good, and something that is less relevant but still relevant about, of course, the ground, right? And if I present the same image, but I should okay, have a look on the bus map, and we just see what have been detected by the same deep structure. I will see that certainly the best one is something like perhaps in the blue sky, or perhaps also on the floor, I mean on the ground, and the less discriminant or the negative evidence of having a bus here, of course, is focused on the plane. That makes sense. Okay, so we can derive this kind of things on many different I mean images for the motorbike, for the sofa, and so on. And okay, I pass for this, and I just want to finish by a comparison to another kind of architecture that try also to do something with region, okay, or with bounding box. Okay, this is my last slide, I think. Okay, and this is the very well-known R for region, CNN. Okay. That have been developed, I think, 1 year ago, and this year, I mean last year in 2000. Yes, okay, last year, yeah, exactly, last year. The fast and the faster, even depending if you were attending to the ICCV conference or to the NIPS conference, you have the fast for the first one and the faster for the other one. But let's say that the idea here is to first detect region by a strategy, an algorithm independent to the deep, okay? And then you go for the deep, right? So you see that typically, I mean, I try to manage my localization, my geometry into the image before going into the deep, right? This is the very main important difference between this approach and the kind of approach I just presented, okay? And so in that case, also typically they need to have the bounding boxes during the train, okay? So that's why it's really, I mean, supervised and not weakly supervised object detector in their case, right? Okay, so I think I'm done. So again, this is more or less the work of, part of the PhD work of Thibaut. And I just also put my face here with specific images of food, just to tell you that if you go on my page and you click on my face, you will directly be redirected to this this demo that we have, because we also apply the algorithm in different contexts, and this is typically something that you can do, of course, with your is responsive, so you can do with your iPhone. Then you take a photo of what you are eating at the moment, okay, and normally, I mean, the iPhone will tell you how to do these things, right? Okay, and this work, of course, there are many codes that is available here, and for the deep version, it will be released in the next month. Okay, so just for in the few weeks, okay, you will have available all the stuff I just presented. Okay, and you see all my student, PhD student, and so on. Okay. The team, and also just an ad about the master that we have that is handled by my colleague Ludovic Denoyer on data science. So of course, if you are a student or interested by that, okay, you can consider this offer, right? Thank you very much.